In 3.3b, we are going to talk about behavior of a graph. Now, if your graph is going uphill from left to right, we would consider that graph an increasing section of the graph. If there is a section of the graph from left to right that is going downhill, we consider that a decreasing section of the graph. And the constant graphs are if there is a horizontal section from left to right. So when we are using interval notation to describe some type of behavior of a graph, that interval notation is going to refer to the x's from left to right. The y is going to be described by the word. So the y's are constant along this x interval from left to right. The y's are decreasing from this x interval from left to right. The y's are increasing from this x interval from left to right. So if we look at our first example, it is asking us to determine the behavior of the graph between the indicated points. So you will notice that these are the x's they're talking about. This word is describing what the y is doing. How is the height changing? So if we start and we look at from A to B, from A to B, we are going downhill. Now, for behavior of a graph, our math bug is always looking to the right. And in this section of the graph, they are going downhill. So that section between A and B is decreasing. Now, they're asking between B and C. He's going to look to the right. He's going uphill. That section of the graph, the y's are increasing. Between C and D, if he looks to the right, that section of the graph, the y's are decreasing. So remember, between the x's of C and D, the y's are decreasing. Lastly, we want to look at the x's between D and E. For the x's between D and E, you'll notice that he's on a nice, flat, wonderful spot. That's a constant. Okay, so please remember that the interval is describing between here and here. That's the x values. What is the y doing? Is it going downhill, uphill, or staying constant? Increasing, decreasing, or constant? So here, what we're going to do is we're going to actually talk about the intervals. Now it says to determine the intervals on which the function is strictly increasing, so just going uphill. So what we're going to do is we're going to do increasing, and we're going to do decreasing. Okay. So I'm going to let's do the increasing sections in green, and I'm just going to highlight them. So those sections were going uphill, and that is an x value of 1 to an x value of 4, and here from an x value of -3 to 2. So we are going uphill when x's are between -3 and -2. The y's are going uphill, increasing. And then again for an x value from +1 to an x value of 5, the x's are increasing. And technically, you know, it's a little better if we use parentheses. And the reason we want to use parentheses is because at that switchover point, at that, you know, little hill or valley in the graph, you're not necessarily increasing or decreasing at those hills and valleys. Okay, so now let's talk about where it is decreasing. Okay, so from an x value of -3 to, no, I'm sorry, that's -5 right here, from there to there. So from an x value of -5 to an x value of -3, our y's are decreasing. And then we can go from an x value of -2 to an x value of 1. They're decreasing. And then from an x value of 5 to an x value of 7, the y's are decreasing again. There are no constant sections of this graph. It's either going uphill or downhill. As far as Alex goes, it says write your interval, or write your answer as an interval or list of intervals. And when writing a list of intervals, make sure to separate each interval with a comma and to use as few intervals as possible. So the answer they would want for the increasing, the strictly increasing, you would do -3 to -2, comma 1 to 5. Let's take a look at a piecewise function. It says, for a piecewise function, only use the appropriate piece or graph the piece in the appropriate place. So, first, I want to talk about what this graph is doing. Between an x value of -2 and -1, including -1, we are at a height of -1. I'm going to draw just a little kind of okay, so let me repeat that. From an x value of -2 to an x value of -1, we are at a height of -1, and we want to include that endpoint. And then from an x value of -1 to 0, we are at a height of 0. So from -1 to 0, we're at a height of 0. We include that one. And then from 1, we're going to be at 1, from an x value of 0 to an x value of 1. And then we're going to be at 2. Don't include the 1, but do include an x value of 2. So that is what's called the step function, if you wanted to see that. Now they wanted us to find h of -1, h of -1/2, and h of 2. So I'm going to show you how to look at it from the piecewise piece, and then I'm going to show you how to look at it on a graph. So -1 is included in the set. Remember, that's your input, that's your x. -1 is included right here. So h of -1 is the value we see right there. So it is -1. And you can go over to the graph. When h is -1, there is my colored in dot right there. Okay. Now, -1/2 is in this region right here. So the answer for that one is 0. And you can see at a height, or at an x value of -1/2, we are at a height of 0. And then h of 2 is included in this region. So h of 2 is 2. And if we drew or went over to the graph, at 2, we are colored in right there. So for a piecewise function, you only plug in the piece in which that particular x value is a member of that particular domain. So -1 is in here, that's our answer. -1/2 is in here, so that's our answer. 2 is in here, so that's our answer. And if you graphed it, it should line up that same way as well. Let's talk about domain and range of a weird function. So remember, the domain are the x's from left to right, range are the y's from bottom to top. And it says to write them as intervals and or unions of intervals. So our x values we start at are -6, and we use that x value. Now, our x values keep going to here, but there's a connection where wherever we left off at -2, this piece keeps on going. So that piece keeps on going to here. And then this piece takes over. So then we have to here, okay? So think about it. I use those x's. I use that. Now I kept going. I'm using those x's. I'm using those x's. Oh, keep going, keep going, keep going. Oh, but there's nothing at 8. So the lowest value is -6. The highest value is 8. I can use -6. I can't use 8. So our domain is from -6 up to 8. Our -6 is included, so put a bracket. Our 8 is not. Now range goes from bottom to top. So the bottommost piece of our graph is here. Let's just say I think that's -7. Okay. So -7, I used all those, I used all those. Now I use that, so I use those, I use those, I use those somewhere. Oh, that's an open circle. Oh, but I used it over here, that's okay. Oh, I use that right here, I use that right here. The highest I ever get, let's assume, is 9. So the range, the lowest I got is -7. There is a closed circle there somewhere. And then I did use 9. There is a closed circle or a section of the graph with a height of 9. So that is the domain and range of a piecewise function. If these pieces did not line up perfectly, so like if this one didn't start over till here, you would have to break those apart. But you want to use as few intervals as possible. So if the intervals connect and one of them is colored in and one of them isn't, you're okay to keep going. Okay. Now let's talk about something called extrema. Now extrema of a graph are going to be the high points and low points. I think of them as hilltops and valleys. Okay, so if we look at this graph here, I see 2 valleys and I see 1 hilltop. So if it is the lowest point of the graph, we call it, so the lowest is called the absolute minimum. If it's just a valley, it's called a local minimum. So if we look at the ones in blue, this one right here is an absolute minimum. This one right here is a local minimum. Local to that area, it's a valley. Now, this point right here, an absolute maximum, is the highest of all the points of the graph. This graph does not have a high point because these are going to keep going up forever and ever. But it does have what's called a local max. A local max is just any hilltop. So local to the area, then it is a hilltop. It is maximum to the things that are right around it. If you are the little math bug and you're walking up there, you are still having to go up to a hilltop. Okay. Now it says to round to the nearest hundredth, use the Alex graphing calculator. Most of the time, the graphing calculators are going to have little dots highlighted highlight the ones that are hills and valleys. So if they wanted a local maximum, that is the only point there. So it's 0.306, 2.759. So that is the answer they would want. To the nearest 100, they only would want 2 decimal places. So 0.31 and 2.76 would be fine. So you may have to use, if you are not given the graph, you may have to use like Desmos. In this question, it says, find the absolute maximum and minimum of the function. Now, these functions don't have arrows on the end here. This one doesn't have an arrow. This one doesn't have an arrow. This one does. So watch whether there are arrows or not. Okay. So it says, if no such value exists, click on none. Assume that the dashed line shown is a vertical asymptote. That just means we will approach that value but never cross there. We just keep getting higher and higher, but we never cross that. Okay. Okay, so is there an absolute maximum of this function? Well, the highest value here is infinity. So as far as absolute maximums, there's none. There's no high point of this graph. The absolute minimum of this graph is the lowest value of all. And if we assume that that hits the point perfectly, that is the point 4, -4. So the absolute minimum of the graph is -4. It's the y value. Now let's look at this one. The absolute maximum, the highest point of this graph is this point right here. That is the point -4, 2. So the maximum height we're ever going to hit is 2. This is an absolute low point of the graph. No point is lower than it. So that is our absolute minimum. And that happens when x is 0 and y is -5. So the absolute minimum is the y value, -5. Now, these here, that is a local max. And these, the endpoints, it depends on how they're defined. This is not included. That's a local max. That endpoint, it's not really defined as a max or a min. One more to look at, example 7. It says, here's the graph of function g. Find all the local maximums and all values, wait, is there more than one to separate? All values at which g has a local maximum. Okay. So I'm not exactly sure the difference between what they're saying here. I think maybe these want the x's and those want the y's. I don't know. But this is a local min. That's a local max. Hilltop. That's a local max. That's a local min. So the maximum values, the local maximums are when x equals -2 and x equals +2. So maybe this would be the local max. I think maybe this is x equals a -2 and +2. And this is that g of x equals the heights at those locations, 0 and 3. I think that's what they want. I'm sorry, we'll have to explore when we get to Alex. And then this is the homework that goes with it. So you're going to find all the local mins and maxes. Where's the function increasing and decreasing? And then I've graphed these here, but you may have to use Desmos to get an accurate pinpointing of those locations. Okay, so that is 3.3b. And then we will talk about more parent information facts next time.